Okay, so in this example, one factor is given right here. X plus 5 is a factor. We're going to factor this completely and find all zeros. Okay, so finding zeros, what we're going to do is we're going to be plugging in 0 for y and solving for the x's. Okay, now you could try to factor this. It looks like it might work by grouping. There would be a common factor there, but there's not going to be one here, and it's going to be a dead end factoring by grouping. This one's not factorable, but that doesn't mean we can't solve it. Okay, so what I'm going to do is I'm going to take x to the third plus 9x squared plus 23x plus 15, and I'm going to divide x plus 5 out of it because I know it should go in evenly. Unless I was lied to, it says that this is a factor. So when I divide it out, I should get no remainder, and then I can see what's left after I've divided out of the original longer polynomial. Okay, I'm going to set this up with synthetic division because it qualifies for that. I'm dividing by x plus or minus something. Okay, and then I'm not missing any terms here, so I'm just pulling those coefficients out. Okay, I'm going to pull down the 1, and then negative 5 times 1 is negative 5. Add these, that's 4. Negative 5 times 4 is negative 20. Add those, and I get 3. Negative 5 times 3 is negative 15, and I got 0. So, hey, it really is a factor. I've now verified that. Okay, but what I was actually doing is taking my original function and breaking it down. Okay, so what I've got left here, this would be 3, 4x. This is x squared. So x squared plus 4x plus 3, that's this, right? So that's what I get when I divide that. So, hey, if I take this polynomial and divide out x plus 5, that's what we got, okay? All right, so this is equivalent to this, right, to that longer polynomial. So now, and you could try it out, you can multiply it back together. You should get x to the third plus 9x squared plus 23x plus 15. Okay, and now I've got it down to something that's a little bit more manageable. Okay, because I can factor this with a diamond problem. So let's go ahead and try that. Looking for two numbers that add to 4, same two numbers multiply to 3. Hey, it's going to be 1 and 3, right? So now that I've got this completely factored, there's no more factoring to do. If I'm finding the zeros, all I'm doing is plugging in 0 for f of x, or y if it's written with a y, and then using the zero product property. So I could have done that at the beginning. It doesn't matter when you do it, but at some point you want to plug in 0 for y, and now I'm going to solve this for x. So one of these three factors has to equal 0. And then so x will equal negative 1 or negative 3 or negative 5. Okay. If I had done the same problem and then I couldn't factor the trinomial that's left, I could have still used quadratic formula or completing the square, and that way even if it involves a radical or an imaginary number, I could still solve for x. Okay. When it is factorable, that's usually what I go for. Okay. All right, so let's try this next one. So this next one, I can't do synthetic division. There is a way to do it, but it's not worth it, I think, because I've got this 2 in front of the x. I've got a coefficient that's not 1. So I'm going to have to use long division here. Okay, so let's set this up with long division. So I'm dividing by 2x plus 1. And then I can see there is a missing term here. So I want a 0x in there, and I want to do that if it's synthetic division as well. Okay, so here's my basic setup. So let's see what happens when we start dividing. So I'm thinking 2x times something equals 6x to the third. Well, 2 times 3 is 6, and x times x squared would be x to the third. So this is going to be 3x squared. And I want to choose where to put the 3x squared. I'm not going to put it right up here. I want to put it above its like term. Like so, okay, and then I'm taking 3x squared and multiplying it back by the binomial. So I'm really distributing it into the 2x plus 1. So that would be 6x to the third, and then 3x squared times 1 is 3x squared. Okay? So next up, I'm subtracting. Remember, we're not adding, so those cancel out like they should. And then don't put 10x squared down there. If you did that, you added them. It's 7x squared minus 3x squared. So I've got 4x squared. Okay? I'm going to pull down the 0x. And now I'm thinking, just concentrating on these two pieces, 2x times something equals 4x squared. That would be 2x. So I want that above its like term right there. And then again, I'm going to distribute back into the binomial. Okay, now I'm going to subtract, not adding, right? So 0x minus 2x would be negative 2x. Pull down the negative 1. And then 2x times something is negative 2x. That would be negative 1, right? So let's hope we get no remainder here. So negative 1 times that binomial. Hey, and then I've got, that's going to be 0, right? I got negative 1 minus negative 1. So negative 1 plus 1 is 0. So I get a 0 remainder there, okay? So now if I take f of x, I've got it down to, I factored out the 2x plus 1. So got it down to this. And now I've got a quadratic trinomial that hopefully I can factor, okay? So I'm going to do a little side problem to factor this. Here, maybe I'll do that up here. Okay, so if I have 3x squared plus 2x minus 1, there's no common factor there. I'm going to do a modified diamond problem. So I'm going to multiply the n piece by 3. Okay, then I'm going to factor this with a diamond problem. Okay, so if I have a 3 and a negative 1, that's going to work out there. So x plus 3, x minus 1. Okay, modify back. So in the beginning I multiply by 3. Now I'll divide the number parts by 3. Okay, I can't reduce the 1/3 anymore, so I'll pull the 3 out in front of the x. And the 1 will just fall to the ground there. So hey, this factors to x plus 1 times 3x minus 1. Okay. So at some point I want to put in a 0 for y. I might as well do that now to save myself a little bit of writing. Okay, now this is completely factored, and that will allow me to solve for x. One of these three things has to equal 0. So if x plus 1 equals 0, then x equals negative 1, right? There's a solution. X could also equal 1/3. Or x could equal negative 1/2. Okay. Okay, so on the next page, we're going to put that together with end behavior to make a little sketch of a polynomial. Okay, so next up, we're going to describe the end behavior of this first off, okay? So this is already factored, so that's great for finding zeros. It makes it easier to find the zeros. It makes it a little bit more difficult to find the end behavior. It'd be nicer if it was all multiplied together, okay? So you could multiply it all together, but I'm not going to do that whole thing. What I'm going to do is just take the first term of each of these binomials and imagine if I did all the multiplying, x times x times x is x to the third, and then I'd have a bunch of other stuff. And I really don't care what the other stuff is for finding the end behavior. Okay, I've got enough information here to find the end behavior. So I can see that I've got a positive leading coefficient. Okay. Positive leading coefficient. Okay, and I've got an odd degree. So I'm just thinking of the simplest possible equation that has those same characteristics. So that would be y equals x, okay, which is going to have, which is going to be a line that looks like that. So this is going to have the same end behavior as that line because it has those same characteristics, okay? So as x approaches negative infinity, so that means as we're going left on the x-axis, we're going to have to go down on the y-axis. So y is going to approach negative infinity. Basically, in other words, as we go left, we go down. As we go right, we're going to go up. So as x approaches positive infinity, y is going to approach positive infinity. Okay, so there's our end behavior. Okay, finding the zeros. Well, hey, this is good news here because I just plug in 0 for y, and since it's already factored, I can get straight to the zero product property. So x would equal -2 from this factor, or x would equal 1, or x would equal 3. Okay, and using these two pieces of information, we can make a very rudimentary sketch of what this function might look like. Okay, so it says no y scale necessary. So this is my y-axis, right? And here's my x-axis. So what I want to do is the zeros are the x-intercepts. So that's going to be where my graph crosses the x-axis, okay? So I want to make sure I plot those points. So I want to, if I go 3 units in each direction on the x-axis, then I got plenty of space here, okay? So I'm going to plot those points, -2, +1, +3, okay? So that's where those are going to cross. What I'm going to do now is use this end behavior, and you actually don't need the fancy mathematical version. I can just think, okay, this is going to start low. So it's going to start down here, my graph, okay, and then it's going to end high up here. So I'm just going to draw a curve that crosses over the x-axis. So let's start it. It's going to start down here. Okay, I'm not worrying about how high this mountain is here. I just know I have to turn around because I got to cross the x-axis again in the next place. Okay, crossing there. And hey, I got to turn around at some point. Not worrying about how deep this valley is either because I'm not worrying about the y scale. But I'm going to turn around and then this is going to end up that way. Okay, so it's got its limits because it's not really telling us what those points would be. But we got a basic sketch of what this is going to look like just using the end behavior and the zeros. Okay. All right. So next up, we're going to find the zeros here. Well, hey, I just plug in 0 for x, and then I take the square root of both sides. But here's the thing. So I'm thinking what times itself equals 0. That's going to be 0, right? The square root of 0 is 0, whether it's the positive root or the negative one. But since I've got, since I can think of this as x times x, if I use the zero product property, I got x equals 0 and x equals 0 again. Okay, so I get the same solution, and in the past that hasn't had any significance, but it actually is going to have a significance. So you can just list 0 twice, but I do want to show that this is a double root. Another way you can list this, if you underline it twice, that means that that is a double root. Okay, a double 0, a double solution. Okay, so likewise over here, this means x times x times x, so zero product property, x would equal 0 3 times, so you can say 0, 0, 0, or you can just do this to show that that is a triple solution there, okay? All right, so I'll get to the significance of that in just a second. Actually, I'll get to it up here. So y equals x squared, that's my parent graph. Okay, so the parent graph for a parabola, right? So hey, there's the vertex. So let's think about this. And then it go through those 2 points, and it would go through 2, 4, and -2, 4. But when it is intersecting the x-axis at 0, right? The significance is that it does a U-turn right there. So when I have a double root, it's going to be a U-turn. So that means it's going to touch the x-axis and turn around, right? Okay, so that's always going to happen with double roots. When you have a triple root, the graph of y equals x to the third, which we haven't covered in here yet, but it's kind of an S-curve. So it's still going to just cross over the x-axis with a triple root, but it's going to be the middle of my S-curve, kind of where the S changes directions, okay? So a triple root's going to look like that, and we won't have to deal with too many of those right now, but that's what's going to happen with a triple root. Okay. All right, so let's get to this next example then. Find the zeros. Okay, so I'm going to plug in 0 for y, and I'm going to solve for x. So looking at this, hey, I can factor this really quickly with a common factor. I can factor out x squared. And boom, it's factored, right? Okay, now solving this, I've got either x squared equals 0 or x minus 2 equals 0. And then I got to remember that x times x equals 0, so this is going to be a double root, okay? Okay, and then over here I've got 2. So here are my zeros. Those are my x-intercepts, okay? Describe the end behavior. So hey, this is going to have the same end behavior as y equals x, right? Positive leading coefficient, odd degree. So it's going to have this end behavior, okay? So it's the same as that one above. As x, as we go left, we're going to go down. As we go right, we're going to go up. Okay, and now let's try making a sketch here. So, not worrying about the y-axis so much. I want to make sure I have room on the x-axis for these. So if I go 2 units out, that's all I need. Okay, got an x-intercept at 0 and another one at 2. Okay, and then my end behavior, I'm going to start down low, and I'm going to finish up here, right? Just like the end behavior here or described there, okay? So now I'm going to try to sketch this. I'm starting down here, but heads up, we got a double root, okay? So you don't necessarily have to write it in like this, but you want to be thinking about that. We've got a double 0 right there. So that means I'm starting here, going towards this, but when I get there, I don't want to just cross over. I just want to touch that and do a U-turn, okay? And now this is a single root, so I am going to cross the x-axis there, and then that puts me in the right place. So there is my sketch. Okay, and again, you know, it doesn't show me exactly where that point is, but I get a general idea of what this looks like. Okay, got one more example on the next page. Okay, so I'm going to find the zeros on this next example. So I'm going to plug in 0 for y. And then I'm going to think about factoring this. Okay, so hey, this is a quartic trinomial, right? I've got a 4th degree trinomial. So this is going to be factorable, this particular one. It's just in the front of my parentheses. I'm going to have x squareds instead of x, so that the firsts give me x to the 4th. Okay, and then I'm going to factor this with the diamond problem. So let's see. I've got negative 12 up here and 27. So I'm adding to get negative 12, multiplying to get 27. Negative 3 and negative 9 is going to be my winning combo there. Okay, and then I can use 0 product property, so either x squared minus 3 equals 0, or x squared minus 9 equals 0. Okay, actually this is a difference of squares, right? So you could factor that further, so I probably should have done that, but that's okay, because I can just add 9 to both sides, and then take the square root. But when you take the square root, remember there's a positive and negative root, so I got plus or minus 3. And that makes sense because this would factor into x plus 3 times x minus 3 over here, okay? I definitely can't factor this piece anymore, but I can still solve it, right? I can just isolate the x squared and then take the square root. Okay, and again, remember, there's a positive and a negative root, okay? So these are my zeros. Okay, describe the end behavior. Okay, so I'm looking at this thinking this has, here I'll write it up here, this has a positive leading coefficient and an even degree. So the simplest equation I can think of, those same characteristics, looks like this. So it has this end behavior. So it's going to start up high and end up high too. Okay, so as x approaches negative infinity, as I go left on the x-axis, I'm going to go down on the y-axis. And then as I go right on the x-axis, I'm going to go, wait, I said down, but I meant up. Sorry, that should go to just going up on both ends. So as I go left, I go up. As I go right, I go up as well. Okay, so those should both be positive infinities. Okay, so let's make our sketch. So no y scale necessary here again, not worrying about how far up and down these curves go, but I am worrying about the x-intercepts and what happens with those. Okay, so I don't have any double roots here. The square root of 3, what I'd want to do is find a decimal approximation of that to make it easier to graph. Okay, so that's about 1.73. Okay, so this isn't going to be that accurate, but I can eyeball where 1.7 would be, okay? So I want to go 3 units to the right and left. 2, 3, 1, 2, 3. Okay, so I've got my y-intercepts at 3 and negative 3, also at 1.7. So 1.7 would be something like this, right? And negative 1.7, something like that. Now those are all single roots. I'm going to start up here. And I'm going to end up here. So I'm not going to do any U-turns on the x-intercepts. So I'm just going to start up here, cross over, okay, and then I see, oh, I need to cross over there, so I better turn around, cross, and then my next x-intercept, going to have to turn, and then I got to turn once more, and I ended up where I was supposed to end up, and I get this kind of W-looking graph. And there it is. And that's it for now. See you next time.